for the neighbors. I didn't think it was that. We can't have them trying to 0 to 4%. Why can't 4%? I mean, so well, I didn't know that you could accept 4%. At first, we voted to accept 4%. But then when you look at the neighbors who are that laid off, hard to say 4% out of his job. What? And
Oh, I know.
Yeah. This is the mic. This goes around the neck. So and then you can just adjust this. So just turn that on. Volume so should be all good. Here you go.
Great.
And just clip on the side.
But we can turn it off now.
Okay, yeah. So making sure I say the first thing correctly, Laurence.
Sure.
It's
fine.
Sorry.
You can say Laurence.
Laurence.
Yeah.
My bad.
The English twist. It's really Laurence, but
Well,
fine.
yeah.
That's too hard.
No, it's just like
When I say Laurence, people expect a guy, so they get confused. So. I don't have to talk over those slides, right? Because these are not my slides.
Oh no, I will do
Okay.
the talking. I'll do the talking here, and then I'll just like switch it to like when it's like your slides stuff. So yeah.
Yes. Yeah, well, just for the currency exchange. Yeah. But it's because they always say, oh. It sounds like, oh, we got a good deal going.
Start. Okay. Hello everyone. Welcome to the TSI public talk here. So here up here, there's like a QR code. If you scan, there's a chance that it's a raffle, but there's a chance that you can win the TSI mug. So if you want to, please scan this. And just a few short questions, but that's about it. So yeah. Anyway, so today's talk is going to be by Professor Laurence. She is the Canadian researcher in artificial intelligence and computational cosmology at UDM and associate member at Mila. And she will give us a talk on is AI going to transform our current understanding of the universe? But right before we start, just a little bit of code of conduct about our events here. So please, we want this to be an inclusive space. So if you feel any uncomfortable or anything, please let me or the volunteer at the door that you have met outside know. And of course, if you have any suggestion or any question, please feel free to email us at the tsi.us-outreach email there. So anyway, I'll let you take over.
All right. Thanks. This doesn't sound like it's working. Is it working? No, right? There's a green light. All right. Is this working now? I hear zero echo, so I feel like it's not working.
It's not working.
It's not working. Now is it working? Oh, it has to be really close to me. Wow, this is going to be challenging. Okay. All right. Can you guys hear me now? Ish, kind of. Okay, let's just hope for the best for the people on Zoom. It's fine?
Yeah.
Okay, they'll be, oh, they're hearing from the owl anyway, so, all right, it's fine then. All right, so that's not my slides. I guess that's the next talk probably. Please come for the next talk. It's gonna be awesome, very entertaining. All right, this is my first slide. Okay, so today I'm gonna be telling you about some of the research that's been going on in my group at the intersection of machine learning and cosmology. So I was told that this was a public talk, so I prepared something that's accessible for everybody when I see my students up there and my postdoc. So, you know, if this is too boring for you guys, tell me. I'm happy to talk about whatever you want. If you have questions, at any point, please feel free to just interrupt me. I can talk to whatever length you want about whatever topic that, you know, I'm going to be mentioning. So, all right. So there's a bunch of stuff going on in my title. So I'm going to be first very honest and tell you that I am not coming from a machine learning background. I'm a cosmologist, so I come from a physics background. So I figure I better tell you what is cosmology first. So cosmology is basically the study of the universe as a whole, its components, what it's made of today, but also how it was born and how the stuff that we see around us today emerged from like the beginning of the universe with like all the stuff interacting together. And then ultimately what's its fate, you know, in the far future. So that's kind of like a very ambitious topic. It doesn't really get much bigger than that, in fact. So, all right, so that's kind of like the purpose of cosmology. So this is the must-have slide in any cosmology talk. So what this slide shows is basically our current understanding of the universe as a whole from like its birth up to today. So it's like the evolution of the universe. So on this slide, time goes from left to right. That's my directions, right? It's good. Okay. And so it shows that basically like everything that we see around us today, like all the galaxies, the stars, you and me, we all started out as quantum fluctuations on really, really, really tiny scales at the Big Bang. And then right after the Big Bang, there was a phase of accelerated expansion of space where those tiny, tiny fluctuations were stretched to extremely large scales. And then they became classical. And then that was the end of inflation. And then the universe at that point was very hot and super dense. And then slowly with the expansion of space, it cooled down up to the point where it went through a phase transition from plasma to gas. And then at that point, the universe became transparent all of a sudden. So there were like light that was emitted at this point. So that's like what we call the cosmic microwave background there, real close to the beginning. And at that point, the universe became transparent. So the light that was emitted at that point just started traveling as time was passing. First stars were forming, light keeps on going, first galaxies form, light keeps on going, all the way up to today, here, when we can capture that light and see it in our detectors. So when we do that, what we see is this. So this picture is remarkably unremarkable. So these are the photons of the cosmic microwave background as seen by Penzias and Wilson in the 60s. And so, yeah, it's remarkably uniform. This is the temperature of those photons. So it took decades of extremely hard work to finally be able to see tiny fluctuations in the temperature of that light that comes from the very beginning of the universe with the COBE satellite in the 90s. And then there was the WMAP satellite, and then finally Planck in the last decade. So as amazing as it is to be able to measure those tiny fluctuations in the temperatures of photons that have been really like traveling from the beginning of the universe, it's really important to remember that this is really, really like homogeneous. The fluctuations in the temperature of those photons are basically just like 1 part in 10 to the 5. So what that means, if we think about it, is that if I look at a photon that's been traveling since the Big Bang from like that direction in the sky, and a photon that's been traveling since the Big Bang from that completely opposite direction in the sky, and I compare the temperature, they're almost exactly at the same temperature. And that's really, really remarkable because there's really no reason why they know that they have to be the same temperature. They come from such separated regions. It's like if we do the calculation in like standard Big Bang cosmology for what's the size of a patch of the universe that would have had to come in like thermal contact to know that it has to be the temperature, it would be about 1 degree in the sky. So that's about this size here. So there's really no reason why 2 photons coming from completely opposite directions in the sky should know that they have to be the same temperature. So that's called the horizon problem. And there's really no reason why they should know that they have to be the same temperature in standard cosmology. So inflation is the theory that was proposed to solve this problem. So the way it works is that it says that there's a phase at the very beginning of the universe of accelerated expansion of space. And what happens at that point is that physical distances grow quasi-exponentially. So what that means, like how does it help us solve the horizon problem? Well, it's a little bit like the loaf of bread analogy. So if you make a loaf of bread at home and you let it rise and you forget about it and then eventually it just takes over your whole kitchen. So what happens is that maybe like your loaf of bread wasn't quite homogeneous like initially. And maybe there were some parts in the dough that were a bit more salty, some parts had a bit more water, some parts had a little bit more bubbles of air. But then if you just let it expand so much that it takes over your whole kitchen, you're going to end up seeing just a tiny, tiny, tiny patch of dough that was homogeneous to begin with. So that's kind of how inflation solves the horizon problem. So horizon problem, check. Okay, so there's a bunch of other problems that inflation solves, but I'm not going to get into those. But if we just go back to this plot here of the tiny temperature fluctuations in the CMB, there's something else that's really remarkable about these things, that like inflation makes very, very specific predictions for what should be the structure of those fluctuations. So if we look at fluctuations of a specific like size and we count how many of those there are, inflation tells us exactly like how many there should be. So we can compare the predictions from inflation and the observations from this patch by looking at different patches of the sizes of patches of fluctuations. And we find an almost perfect agreement between like the theory, the prediction from the theory and the experiment. So that's considered by a lot of people as one of the biggest successes of modern cosmology. All right, so that's pretty good. Another thing that's also pretty cool is that inflation also makes very specific predictions for like, the size of those patches. And it also tells us that based on like the size of the fluctuations, we know that there should be some invisible form of matter that doesn't interact with light. So basically transparent matter. And just by looking at the shape of the fluctuations, like how many fluctuations there are and how big they are, we know that there should be about 5 times more of that invisible matter that doesn't interact with light compared to the regular matter that makes up like the atoms that we're made out of. And that invisible matter is what we call dark matter. And by looking at those fluctuations, we know about approximately how well it should be distributed in the universe really, really early on in the universe. But we know that today the universe doesn't look like this. It doesn't look like a super homogeneous soup. It's very homogeneous. There's a lot of stuff around us in the universe. There's galaxies, there's stars. It's like there's a bunch of stuff happening. So do you understand how that happens? What we do is that we basically distribute matter, and specifically dark matter, the way that we see that it was distributed according to the CMB, and we just run simulations on computers where we just let gravity do its job. So this is what I'm showing here, just to make sure that the fluctuations are right. So like initially we see that the universe is very, very homogeneous. And then as time passes, gravity starts, like places that start out a bit denser, initially they start attracting more matter. And then we form some nuggets of matter. And those nuggets of matter are called dark matter halos. They're called halos. And so our theory of galaxy formation tells us that it's at the heart of those halos that galaxies are going to form. So bigger nuggets, bigger halos are going to form bigger galaxies because they're going to attract more matter. And smaller nuggets, like smaller halos, they're going to form smaller galaxies because they're going to attract less regular matter. So now that we have a way of explaining the structure of the universe that forms around us, we can compare that to our observations today around us by looking at the distribution of galaxies. So here I'm showing a flyby through another one of those simulations that just has the dark matter. And we can compare the distribution of those dark matter halos, the nuggets, to the distribution of galaxies that we see in surveys. So that's a flyby through real observations of galaxies. And if we compare the two, we find, again, that there's an almost perfect agreement between the theory from the prediction and our observations in practice. All right, so this is basically our 2 first ingredients of the model of cosmology: inflation that gives us the initial conditions of the universe, and dark matter that tells us how the structure is going to form. So if we go back to our timeline of the universe here, right about here, there's something that's a bit weird that's happening. Like initially, it was going kind of like the space curvature of the universe was kind of going like this, and then it starts going the other way around like that. So what happens here is that the expansion of the universe starts to be dominated by something new that we call dark energy. So dark energy was first discovered by looking at the explosion of stars that are called type 1a supernovae at the end of their lives. But since then, its properties have been measured by a bunch of different surveys of galaxies, and it seems like it's what's explaining this expansion, this new phase of accelerated expansion in the universe. So if we put all of that together, what we get is our standard model of cosmology, which we call the inflationary lambda CDM model. It's kind of a mouthful. So what it means is that basically the initial conditions of this model are driven by inflation, which is the thing that seeds like the initial perturbations in the universe. And then today, the universe around us is made out of about 70% dark energy, about 25% dark matter, and just 5% regular stuff. So that's the stuff that like atoms, all the stuff that we're made out of, like you and me and the stars and the planets and gas and everything that we've ever seen, that's just 5% of the energy density in the universe today. And that's great, because what I've been telling us so far in this talk is that this explains basically every single observation that we have made of the universe today. So at this point, we can say, good job. So are we done with cosmology? And so we can just go home, right? We have explained everything. And the answer is like, well, obviously not, right? Because like we don't understand any single of the main components of that model. So for inflation, we have no idea what's the field that's driving inflation. We don't understand what it is. For dark matter, apart from the fact that it gravitates, we have never measured any of its properties. And for dark energy, we really don't have any idea of what it is. So that's kind of not a very satisfactory understanding of the universe, really. And so in the next decade, there's a new generation of sky surveys that are entering, that are starting to take observations, and new generation of instruments. A bunch of those have already started taking data. And that's really exciting, because at some level, a lot of the goal of these new instruments is going to answer these questions about the nature of those fundamental components of the standard model of cosmology. And the real theme that's underlying out of this new observatory is data, because the volumes of data that's going to be taken by these experiments is really unprecedented in astrophysics and really in any field. So at this point, I think it's fair to say that what's going to be driving the next generation of discoveries in cosmology is really this big data. And so that's where the challenge and also the opportunity lies. It's a challenge because the traditional methods that we've been using to analyze data in astrophysics and in cosmology are just not going to be sufficient anymore. But it's really an opportunity because machine learning in the past 10 years has really shown that it has the potential for helping us analyzing that data and extracting as much information about our universe as we can. All right. So for the rest of my talk, I'm basically just going to be going through the main components of the standard model of cosmology one by one and tell you how machine learning is going to help us understand it better. Does that make sense? Yeah? Good game plan? All right. Do you guys have questions at this point? No, it's good. Perfect. All right, so let's start with inflation. Okay, so inflation is, okay, let's go back to like the basics. So space is expanding. This is the expansion of space. So what it means is that if I lay out some like system of coordinates in space with like, I just mark down in space, this is 1 meter, 2 meter, 4 meter, I just lay out a grid of coordinates. With the expansion of space, what's going to happen is that this system of coordinates is going to expand with time. The whole thing is going to become bigger. So if after a while I come back and I measure the distance between points, it's just going to have grown. Like the distance just grows, not because things like fly apart from each other, but it's because space itself is constantly becoming bigger. Okay, so that's just like regular expansion of space. That's what's happening like right now today. And that's what's been happening since the beginning of the universe. But in inflation, what happens is that this expansion is exponentially fast. So I mean that this like function that I have to multiply to get the distances is an exponential function. It's like really, really, really fast. Okay, so that's what inflation is. But what I did not tell you, and it was on purpose, is that I didn't tell you what to make in the model of the universe to make that happen. I didn't tell you how to make that happen. And the reason for that is that there's a very large number of ways to make that happen. There's a lot of models to make inflation happen. So here I'm just showing a very small fraction of those models. I made that a really long time ago, so I'm sure this has grown a lot since I stopped working in this field. But there's a lot of different models to make inflation happen. So the goal here is basically to try to make predictions for things that we can observe from all of those models and compare those with observations, try to figure out which model or which class of model is correct, and then figure out which extension to the standard model of particle physics is correct. So basically, we want to learn more about fundamental physics and learn how to what extensions of the standard model of particle physics is correct. So so it's really important to be able to make these calculations very accurately, because in the next decade, there's going to be a bunch of, well, this is outdated, this slide, but in this decade, there's going to be a bunch of new experiments that are going to be testing those predictions with unprecedented accuracy. So nothing that I really talked about has anything to do with machine learning so far. But in fact, it is related, because one of the observables that these observatories are going to be going after is the B mode of polarization. So the light that comes to us from the CMB is actually polarized. And what we want to be measuring is a specific mode of polarization for that light. But the problem is that this light comes to us from the very beginning of the universe. So it has to travel through the entire universe to get to us. And specifically, it has to travel, to go through our own galaxy. And there's a lot of sources of polarized light in our own galaxy. And so that's a very large source of contaminant. So we have to understand all the sources of polarized light that comes in between us and the CMB to be able to really extract the signal that we want. And that's extremely, extremely difficult. So the way we want to be using machine learning here is we want to try to make better models for these foreground contaminants to be able to extract more information from the data that we're going to be taking to understand better the predictions, that if we can to test better predictions of different models of inflation, to distinguish them better, basically. So I'm not going to go further in this topic, but I'm going to come back to it at the very end of my presentation. Is that good? So if there's no questions about this, I'm going to move on to the second component of our standard model of cosmology, dark matter. Right? Okay. So dark matter, I've talked a little bit about it so far, but let's go back to what are the evidences that we know of that there is something like dark matter around. So the first person to discover, to realize that there was something fishy going on with gravity was Fritz Zwicky, who looked at clusters of galaxies. So clusters of galaxies are basically groups of galaxies, like the one I'm showing here. There's not a very good contrast there, but this is a bunch of galaxies and they're all orbiting each other. And so by looking at how fast they're orbiting around each other, you can have an estimate for how much mass there should be in a cluster, because if there was not enough mass, they would just be flying apart from each other. There wouldn't be enough mass to keep them in orbit around each other. So he did that, and then he computed the mass that he needed in the cluster, and then he also looked at how mass he could see in stars and gas in those galaxies. And he realized that he needed about 5 times more mass that he couldn't see through his telescope to hold the cluster together than what he could see in stars and gas. So there seemed to be this form of invisible matter that was needed to keep the cluster glued together. Okay, and then a couple decades later, there was Vera Rubin, who looked at individual galaxies. So inside individual galaxies, stars are in orbit around the center of the galaxy. And you can do the same thing. You can look at how fast they're orbiting around the center of the galaxy, and then measure how much mass there should be inside the galaxy to keep the star in orbit without it flying apart. And then again, you find that for stars to stay in orbit at the speed that they're going around galaxies, there needs to be about 5 times more matter than the matter you could see inside those galaxies. So in the 70s, this was the best evidence of something like dark matter that should be holding the galaxies together. There needed to be this invisible form of matter to hold clusters of galaxies and galaxies together, so that all the galaxies and the stars would not just fly apart from each other. Okay. So, and then since then, there's been a lot more evidence about, so for something like dark matter, there's, for example, the CMB that I talked about earlier in my talk that needs to be there to explain how the amplitude of the fluctuations that we see initially in the CMB. And so at a bunch of different scales, there seems to be this invisible form of matter that's needed to hold the stuff that we see together. And there needs, at all these different scales, I said of the whole universe, the scale of clusters of galaxies, the scale of individual galaxies, there needs to be about 5 times more of this invisible matter than regular matter. And so the question here is really, what is that? So of course, as physicists, we have some like ideas for what it could be. There's a bunch of different theories, but I think the leading theory is really that this is a new kind of particle that just does not interact with light. So that makes it completely invisible. And but then it has a mass, and so it gravitates, and so that's how it can explain all these observations. It just doesn't interact with light, so that's what makes it invisible. So it should really be called invisible matter, not dark matter. It's not really dark, it's just transparent. It's like transparent matter. Okay, so since we think it's a particle, then the race is on to really find this particle in the lab and give it a new name and win a Nobel Prize. So there's been a very long history of people building detectors trying to find this new particle. So there's one of those on board the International Space Station that's been waiting to detect this particle. There's also a bunch of those buried deep underground in abandoned mines. They build detectors and they try to find this invisible particle. And it's been a very long time, and they have found nothing so far. So in the meantime, as astrophysicists, we say, well, could we measure something more about this new particle that would give us clues about where to look to find it directly in a direct detection experiment? And so one thing we can do is that we can look at what's its temperature. So how do we look at its temperature? Well, a little bit like for clouds. So if we look at clouds, we know that clouds have different patterns. Some are very smooth, some are very clumpy. And if we measure their clumpiness, we can say something about their temperature. So it works a little bit like that for dark matter. If we look at how clumpy it is, we can infer something about its temperature. So we know that on really large scales, like scales of clusters of galaxies with like many, many galaxies, it really looks like it's extremely cold. But we have never really looked at scales smaller than individual galaxy to see how clumpy it is. Maybe it's kind of warm, maybe it's kind of cold. So we really need to go look inside individual galaxies to see how clumpy the dark matter is. And nobody's ever looked there. To look there, it's very difficult because it's transparent. So we cannot rely on light to know if it's there or not. We have to look at something that's sensitive to what the property that we know it has, which is gravity. So if it's very clumpy, it's going to have gravity of something very, very clumpy. And if it's very smooth, it's going to have the gravity of something that's really smooth. Okay, so the effect that we need to look there is something called gravitational lensing. So this is an example of a gravitational lens. So strong lensing is the phenomenon that we're looking at here, is basically the formation of multiple images of some distant object because its light rays are deflected by the gravity of some intervening structure. So gravity, we know that it bends the trajectory of object. Like if I take I don't want to drop my phone on the floor, but if I take my pen and I drop it on the floor, the gravity of the Earth is going to deflect its trajectory. It's going to fall down, right? So if I throw it like this, it falls on the floor. It was going straight and then it fell on the floor. So light actually does the same thing. So if I throw a ray of light this way, it's going to fall a little bit towards the Earth. But it's so small that we never really see it in everyday life. But when something as massive as a galaxy is there, it's going to bend it a lot, and then it creates an effect that's observable. So if I have two galaxies here, like here on the Earth here, and there's two galaxies, one is right behind the other one, what's going to happen is as the light rays of the background galaxy, they pass near the foreground galaxy, they get bent. And so they come to us from different angles. And then here on the Earth, what we see is multiple images of the same background galaxy. Okay, it's a little bit like looking at a fish from the corner of a fish tank. This is my April Fool's fish. It's not a joke though, but okay. So when we look at the fish from the corner of a fish tank, you can see multiple images of the same fish. Okay, so here I have Mr. Mango demonstrating the effect. So when he comes to the corner of the fish tank, you can see two images of the same fish. Okay, and so it makes an image that's really similar to actual images of strong lenses. So here's the real strong lens. So we see two images in blue of the same background quasar because its light's been bent by the gravity of the foreground galaxy in orange. Okay, so that's exactly the same thing that happened here, is that what's causing the bending of light in the case of strong lensing is gravity, as opposed to refraction in the case of the fish tank. All right, so here are some other examples of strong lenses. And we see that it keeps on making these arcs around the foreground galaxy, like the blue arcs or the background galaxy. And then the reason for that is the geometry of the lens. Okay, so you can actually reproduce an effect like that at home with a wine glass and a fish and a candle. So for this experiment, I made a little video to show you how it's done. So you're going to need a wine glass and also a candle. And it also helps if you have a little bit of wine maybe, and maybe also a buddy to drink with so that you don't drink alone, because that's always sad. So if you dim the lights to make the atmosphere a little bit more romantic, and then you pick up your glass to take a sip, you can look at the flame of the candle through the foot of the wine glass, and then as they become aligned, you see that it's sort of the image of the flame of the candle wraps around the foot of the wine glass. And then it makes an image that's really similar to actual images of strong lenses that we see in the sky, like this. Okay. And so in this analogy, the foot of the wine glass is the foreground galaxy that's bending the light, and the flame of the candle is the background galaxy that is being deflected. Okay, so what we want to do is that we want to use this effect to map out how mass is distributed in the foot of the wine glass, in the foreground galaxy. So basically, we want to figure out if the foot of the wine glass is really smooth or if it's really clumpy. It's a little bit as if there was a bunch of droplets of water on the foot of the wine glass. What's going to happen is that they're going to cause an additional level of distortion in the image of the flame of the candle. See here, like the droplet of water that's there is not, it's kind of invisible. It's not really emitting light. Our eyes know that it's there because it's causing an additional level of distortion on the image of the background candle, and that's what allowing us to infer that there should be something there. Okay, so that's what we want to do with strong lenses. But obviously, in the case of strong lensing in the sky, the effect is extremely subtle, so it's very difficult to model. Okay, so today, well, this set is a bit outdated. Like a couple of years ago when I was giving this talk, we knew of about 500 strong lenses. Now we know a couple thousand strong lenses. But in the next few years, we're predicting to discover about 200 new strong gravitational lenses. And so that's really cool because it's going to give us a lot of power to make this measurement like super significantly in a bunch of different places in the universe to figure out like, is our lensing galaxy smooth or are they very clumpy? But then the problem is that doing lens analysis is really slow. So it takes about 3 days to analyze one lens. So if we scale that to 200,000 new lenses, it would take about 1,400 years to finish the analysis of all the LCC lenses, the new lenses that we're going to be finding. So clearly, this is not doable. I have a bunch of students and postdocs here. And so I don't think they want to be doing this for 1,400 years. So, and even if I hire like 100 of them, it would still take 14 years of them if they don't eat or have weekend or sleep or anything like that. So I don't think that's what they signed up for. So they don't want to be spending like 14 years, 24 hours a day doing this. So clearly this is just not going to work. Like we need to do something else here. And so what we can do is we can do machine learning. So, but like, let me first explain to you why is it that like it's so long to analyze lenses. So I said that I have some data and I want to infer like if the foot of my wine glass is smooth or if it's very clunky. So what I need to do is I need to do two things simultaneously. I need to figure out what's the shape of the undistorted image of the flame of the candle, and I need to figure out what's the foot of the wine glass. Okay, so to do that, the way it works is that I take like my flame of candle. I do an hypothesis. I say, okay, let's say I have this flame of candle and I have this foot of wine glass. I can predict what would be the image. So that's really easy. I just take those two things, I put them in my simulator machine. That calculates the deflection angles, and then it applies them to the image of the flame of the candle, and then I get a lens image. And voila. So that's the simulation process. The problem is that when I have data, I neither know what's the shape of the foot of the wine glass nor the image of the candle. And the problem is that I don't know what's the inverse function of my simulator. I cannot go straight from the data to the parameters that I want to have. So what I need to do then is that I need to pick an image of a candle, pick a shape of a foot of the wine glass, and then make a simulation, compare it to my data, and say, okay, is this close to the data that I saw? If it's yes, then it's good. If it's not, I need to do it again. And I need to do it again and again and again and again until I figure out what's the image of the flame of the candle and what's the foot of the wine glass that give rise to the data that I have. So I do this comparison through like a measure of similarity that's called the likelihood function. That's not really important, but the important thing is that this is super inefficient. I need to do so many simulations to figure out what's the right flame of candle and what's the right foot of wine glass that basically I need to do like millions of those simulations. And then all the simulations I ran, they're completely useless for the next lens I'm going to be trying to model. So this makes it that this is the reason why it takes like 3 days of a person's time to do a single analysis with traditional methods. So basically what we're going to be doing is we're going to be saying, okay, I can model this inverse function using the fact that neural networks are known to be universal function approximators, which means that there is a function that I don't know that's the inverse function of my simulators. So I'm going to be training a neural network to learn that inverse function and go straight from my data to my parameters of interest without having to do all of those simulations. So the kind of neural networks that we do use is something that's called convolutional neural networks, and that's exactly what they do. So those are actually pretty common nowadays around us. They're in self-driving cars. This was analyzes like the street to figure out what are the objects that are in the street. They're also in your iPhoto app to find like people in your photos. So this is what's identifying the person in your photos. And so basically what we want to do is we want to take as an input like an image. And instead of making it figure out like, is this a cat or a dog? Like, what is it that's in the photo? We want to make it predict parameters like numbers that describe what's in the photo. So in this case, we might want to know what's the age of the dog, what's his weight, like all these kinds of things. So Spark is a very old dog, and he's also kind of chubby, so it's a bit fat. But yeah, so this is what we want to do basically. So in our case, what we want to do is we want to input images of strong lenses, make them go through the neural network, and then have them predict the parameters that describe how mass is distributed in the foot of the wine glass, something like the mass of the lensing galaxy, if it has an ellipticity, an angle, the position, those kinds of things. So the way we do that is we train those neural networks just like we would train a baby to figure out what things are by showing a bunch of examples. So we do the same thing with strong lenses. We show them a bunch of examples and we tell them what's the parameters that we want to have. And then these are examples of simulations that we ran to train a neural network. And then we can train a neural network and then we test it on unseen data that it's never seen before. And this is what we get. So here I'm showing the prediction of the neural network on the y-axis and the true value on the x-axis. And you see that it's pretty good. Like it gives a pretty good answer. Like the two match really well. But the main thing here is that this is 10 million times faster than traditional methods. So instead of taking 1,400 years to analyze all of the LSSC lenses, this would take half an hour on my laptop. So this is really a game changer. So now we really can do this. I don't have to make you work for 1,400 years analyzing lenses. So this is good. And so this is super promising, but then the problem is that this is assuming that the foot of the wine glass is very simple. So it can be parameterized by like a handful of numbers, like a position, ellipticity, and angle. But real galaxies are a lot more messy than that. And like specifically in our case, we want to find if dark matter is clumpy or not. So we want to find how like tiny small fluctuations in that lens. And so we need a much more flexible parameterization. So for example, we would need to have some pixelated image that describes the density in the foot of the wine glass, like predict every single pixel value of the density in the foot of the wine glass instead of just a parametric model. So with the years, we have trained these things. It's some complicated architecture, that's not important, but then we have managed to get very good modeling neural network that allows us to predict an image that tells us what's the mass distribution in the foot of the wine glass. So this was super promising, and it's really allowing us to do things that we would have no way of doing with traditional methods. So like, for example, these lenses, usually in my talk, I like to show comparison between like machine learning method and traditional methods. But here I can't do that because I cannot model those lenses with traditional methods. It's just like not possible. So this is really allowing us to do things that we would have no way of doing with traditional methods. So it's super promising, but then there's one thing that's a big problem. The problem is that we have no idea what are our uncertainties. Like what are the things that we know very precisely and what are the things that we have no idea if it's correct or not in those images. So that's the problem of uncertainty quantification. And it's a really big problem with machine learning methods. Basically, if we're going to be doing science with machine learning, we need to embed machine learning models in a statistical framework that allow us to know the precision of our measurements and basically allow us to combine different measurements in a way that makes sense in a statistical sense. So it's a bit technical, but in recent years in my group at University of Montreal, we have been investing a lot of efforts developing methods that allow us to do this quantification of uncertainties in a way that is rigorous and in a way that allows us to model multiple different lens system and combine them together in a way that we can get rigorous like measurements. So this has been shown that it's possible to do on simulations. here. And so these are measurements basically that show that we can combine the measurement of compiness of lenses in multiple different strong gravitational lens and combine their uncertainties together to measure the temperature of dark matter. So this is on simulations, and it's kind of in idealized scenarios that are not super realistic, but it shows that in principle it's possible, and it's something that would have absolutely not been possible to do with traditional methods. So now I have students. This is one of those students who are working on making these simulations more realistic and making predictions for what are the kind of constraints that we can hope to have with realistic data from this new generation of telescopes. So, yes. That's an excellent question. Okay, so the temperature is not really like temperature in the usual sense. So it's basically so it's really a sloppy way that physicists talk about it to talk about the mass of the dark matter particle. So basically, if we assume some level of interactions with the rest of the standard model particles, not through electromagnetic radiations, but for example, through the weak force or other forces of the standard model of particle physics, there can be some thermal equilibrium established with the rest of the particles of the standard model in the really, really early universe when things were really, really hot. But at some point, those interactions stopped. And the point where it stopped is when the universe was at a certain temperature, and that is linked to the mass of the particle. So the more massive the particle, the earlier in the universe that happened. So the hotter the universe was. And so, yeah, that's kind of like how it's related to the temperature, but in a really sloppy way. But it has to do with like, so we talk about it at temperature because it has the effect of temperature. So when you have something that's really hot, it's going to erase a lot of fluctuations on really small scales. And it's going to preserve really large fluctuations. And the hotter something is, the more it's going to erase fluctuations on larger and larger scales. And the colder it is, the more fluctuations there's going to be on smaller and smaller scales. So this analogy sort of holds for dark matter models. So when we talk about cold dark matter, there's going to be a lot of fluctuations on really tiny scales. But as we increase the temperature of the dark matter particle, so as we make its mass smaller and smaller, basically it's going to erase fluctuations on larger and larger scales. Does that make sense? Maybe it was too technical. Okay, so yeah, so basically it's really like so when we consider like a warm dark matter model, there's not going to be fluctuations on like very small scales. So it's going to look like the glass of the foot of the wine glass is more smooth. And when you look at cold dark matter, it's going to be super, super clumpy because we preserve fluctuations on really tiny scales. So the colder the dark matter model, the more clumpy the foot of the wine glass is, and the hotter the dark matter model, the less clumpy it's going to be. It's going to have larger scales fluctuations. And if we make it too hot, then we would even erase galaxies. So we know it's not too hot, can't be too hot because we know we have galaxies. Okay, all right. More questions? Nope. All right. So so this is work in progress. So this is working really great on like predicting what we should see with new telescopes like LSST. So I hope that I've convinced you that like in the next years, we're going to be in a really great spot when this data starts like coming and being available, then we're really going to start making extremely good constraints on the properties of dark matter and measure new things about dark matter. So I don't know how I'm doing the time. This is good. So this is what I had to say about dark matter. Yes.
So you have been collecting data. You have a process to collect data.
Mm-hmm.
Okay. And you say that the hot stuff is, you should have a good understanding of the hot stuff because it's got a lot of the uncertainty is less. So is this giving you any hints as what the dark matter might be? Like, are you starting to get a bit of a sense of it?
So we have
Like, I get a sense you're going to analyze.
so it cannot be like it cannot be too hot but we have never detected. So we know we have ruled out really hot temperature, but we don't know what it is. So there's still a range of temperatures that are allowed between warm and cold. Okay, so we have never detected measured the temperature really. So this data has not really been taken. So we have simulations to say, okay, if it were this temperature, this is what it would look like. We can do simulations in the computer, but it's not real data. It's not the same thing. So the data is being taken like right now. So the data, the LSST started operating. So we started getting data. So they started taking data in the end of June last year. We got the first like internal data in like September. And so, but it's like very, very limited. So there's not enough really already to be able to see anything. So it's really like we have to let the time for the telescope to like take the data, collect the data, and then it's going to become available. And then we're going to be able to like say a lot of exciting things. But we know we're going to be in a good position to do all these exciting science because we work on simulated, like we just do simulations of data. And then we test to see that we can actually do the measurements that we think we're going to be able to do in real data. But like, of course, when there's real data, it's always more complicated than what you think it's going to be. So it always takes a bit more time, but we think we're ready. Any more questions? Yes.
We've gotten very good at separating out different visible light
Yep.
wavelengths and recombining them and colorizing them so that we can actually see an image. How do we separate out differences in the dark matter emissions?
Mm-hmm. Mm-hmm.
Like how do we form an image? How does the LST
Yeah. So dark matter is actually invisible. So we're not going to see it the way we see stars. We only see it through the gravitational influence that it has on other things. So for example, it's just like when we had the glass in the fish tank, we couldn't, like the glass is completely transparent, but we know that it's there because it's bending the light of the fish. And we know that there's not really two fish, there's really just one fish. So we know that there has to have been glass in between to bend the light to make us see two fish. So it's the same thing in lensing. We don't really see the dark matter, but we know that there has to be something there to make these arcs because we know that there is no real galaxy in the shape of a perfect arc like that. There's no like 4 different images of the same thing repeated exactly like that in the universe. The only way this can happen is if there's a clump of invisible matter, dark matter there, that's bending the light to make that happen. So the way that we are inferring the property of dark matter is not by seeing it, is by inferring its presence through its gravitational effect on other things. And the thing that's really good about lensing is that it's achromatic. So what that means is that it affects all the different wavelengths in the same way. So if I look at it in like blue light, it's going to be the same bending as if I look at it in red light, and as if I look at it in submillimeter light, in microwave light, or in X-ray. It's going to do the same bending regardless of the wavelength. So that really helps us doing the modeling like that because we can put all the wavelengths together and it increases the signal.
the images that we get, say from JWST, are we filter.
Yeah, it's in different filters, different wavelengths, yes.
And from them, we combine them in different and imaginative ways to.
Yeah, we can do that, or we can also analyze them separately. So we don't have to combine them. We can say, okay, it has to be the same mass that affects all those different wavelengths of like the flame of the candle in the same way. So it's as if we had multiple different images of the flame of the candle. And we can, but we know that the mass that's there, the dark matter mass that's there has to be the same across the different filters, across the different images. So we can independently analyze them individually, or we can combine them all in just a single image. So we can do either of these things. More questions?
Also produce these multiple images.
Some other objects?
Like, if you have a star that's behind the star, and
Yes,
the gravity.
yes.
So how do you know which ones are caused by gravity, and which ones are caused by the?
So it's the same gravity. It's the same thing. It's just that the stars, we can see them. So we know by looking at like how much bending has been, we know how much mass, regardless if it emits lights or not. Like it, regardless of the source of the gravity, we know how much like mass there has to be in there. And now some of it comes from the stars and the gas. But then if we add up all the stars and all the gas and all the black holes and all that stuff, there's just not enough mass to explain all the bending we see. So the missing part is the dark matter. So yeah, and there's about 5 times more missing stuff than the stuff that we can count by counting all the stuff that we know of. Okay, and like it could be that those like tiny like clumps, they're not pure dark matter. They might have some star in them, but we just can't see them because either those like they're too faint because they're too far away, so we cannot really see them, or maybe in the process of galaxy formation, because these tiny clumps are like orbiting the main galaxy, they were stripped of their stars and there's just very few that are left by like tidal effects. So it could be like a bunch of these things that make them very, very difficult to find. But we're not relying on the light, we're just relying on the mass. So we can find them if they have like stars in them or if they don't. And like another question that we can ask later once we have started being able to detect them is like, okay, so what's like, if we start like really looking in detail at where they are, can we find the ones that have stars versus the ones that don't? But that's like down the road. Once we have been able to find them, we can ask those questions. More questions? No? All right, let's move on to dark energy. Okay, dark energy. All right, to talk about dark energy, we have to do a little bit of thinking about what its effect is on like regular matter. So let's say that I'm on the Earth and like I throw a ball. I expect that like, or my pen that I threw over there. Like if I throw my pen in the air and I expect that it's going to slow down as it's going up and eventually it's going to stop and come back down, right? So that's like gravity on regular matter. So if I have really, really strong arms and I throw my pen like really fast, it's going to go higher up. Eventually it's going to come back down. But if my arms are really, really, really strong and I throw my pen sufficiently fast, it's going to reach the escape velocity for the Earth, and it's going to happen to it the same thing that happened to the rocket earlier tonight. So it's going to reach the escape velocity of the Earth, and it's going to go in space and just never come back. But it will slow down on the way up because of the gravity of the Earth. Okay. So what happens with dark energy is that like you throw the ball up, but instead of the ball like coming down, not only does it not go down, it also doesn't slow down on its way up. It just keeps on accelerating upwards. So it's kind of like contrary to our intuition about how gravity should work. It's really weird. Another thing that's really surprising about dark matter, dark energy, sorry, is the fact that it doesn't dilute with the expansion of space. So like when I have regular matter and I put it in some volume and then I make the volume become bigger, the density should dilute, right? Because the amount of stuff that I have is conserved. So if I make the volume bigger, the density has to go down. Dark energy is not like that. If I make the density, if I make the volume bigger, the density remains constant. So it means that as space is expanding, there's always more of it in the universe, which is extremely weird. And it's unlike any other thing that we know of in the universe. Okay, so it really takes some time to like wrap your head around this because it's really contrary to our intuition about how it should work. The density remains constant, does not change. So it's like, it's really weird. So it's like it does not conserve energy at all.
So the conservation of energy.
It does not conserve energy. It's very weird, very, very weird. Okay, so to try to like understand like how should we understand this in like in terms of physics, like should this be like should we just modify the way gravity works? Should we have new kind of matter that acts in ways that we have never seen before? So how to explain this, right? So what we have to do, what we want to be doing is we want to be looking at this phase of the universe where it starts dominating the expansion of the universe and driving the expansion of the universe, and study how the expansion of the universe like happened in that phase of the universe really carefully to try to figure out like how we need to modify our model of like if we need to modify our model of gravity or if we need to introduce new matter to give us clues as to how we need to change our model of physics to fit these observations. So yeah, so we want to basically measure exactly the expansion of space, how it happens throughout this period of history. And we do that by making observations of galaxies that give us information about how space was expanding in this phase. So this is really similar. The way we do this is really similar to like the graph I was showing about the simulator for the gravitational lensing. So we have like initial conditions for our universe and a bunch of parameters that describe how how the evolution of the universe happens. We put that in our universe simulation machine, and then we get out a bunch of observations, like for the distribution of galaxies on really, really large scales. And then we have to compare those to observations. The difference here is that when I was doing strong lensing simulation, the simulation was really fast. Here, the simulation is really expensive. So doing a bunch of those simulations is almost impossible because it costs like 200 million CPU hours. So this is clearly not something that we're going to be able to run a lot of. So here I'm showing one of those simulations. It's called the it's called the Illustris TNG simulation. And yeah, this one costed 2 million CPU hours to run. So we have one. So we're not going to be able to. So if we want to test a bunch of different ideas for different dark energy models, we have to really make sure that we use this simulation budget very carefully and we think about it in great detail. So that's like the first. So basically, the place where we want to use machine learning is to try to understand better how do we connect our cosmological parameters like that describe the nature of the components of the universe and how they influence how it evolves, and then our observations, because that's what we want to quantify. And then the other place where we have issues we need to solve is foreground contamination. So it relates to what I talked about at the beginning of the talk, because we have the galaxy, our own galaxy, that's in the way of all those observations of the universe we want to make. And so for a lot of those probes that we want to use, this is what the universe looks like. And in this case, so this is mostly the galaxy really that we're seeing here. So the galaxy is about 10 to the 5 times larger than the signal that we want to measure. And so we're looking for, it's 10,000 times bigger than the thing we want to measure. So it's very hard to remove the galaxy for a lot of those things. So in both of these things, machine learning can help us. All right, so let's think about this. All right, so machine learning is going to help us in the first case by figuring out how we can accelerate this forward simulator of the universe, like the simulation machine. And then in the second one is going to help us model better those foreground to figure out how we can subtract them better. Okay, so this is work that's in collaboration with a bunch of these institutions. It's a collaboration that's called Learning the Universe. It's funded by the Simons Foundation. And I'm just going to give a really brief overview of some of the things we're thinking about with machine learning. So the first one is like how to accelerate this like universe simulator machine. So usually we split that into 2 different problems. The first one is just simulate just the part that has the dark matter, because that just interacts to gravity. It's way easier. And then after that, you just add the galaxies on top, because that's what we can see. So if we split it like that, it makes things much easier. Doing both things at the same time is really, really hard. So we're not going to do that. So just doing the dark matter part is something that you could think of doing with a neural network. So you can do a bunch of simulations, train a neural network, the same thing that we train to predict the parameters of our strong lenses. So basically, you take your initial conditions, put them in a black box, you get out a universe. We're done. This is great. But then the thing is that we don't see just the universe at one specific time. We see it throughout multiple times in the history of the universe. Because when we look far in space, we look far in the past, because it takes light some time to get to us. So we always see things that they were far in the past. So the further away we see when we're looking at very distant galaxies, the further back in the past we look. And it's really hard to train one of those things to predict consistently what the universe looked like across different times. So that's not super good. Also, it takes a lot of data to train one of these things. So actually, you're not really saving much on simulations. Like you could have just done your analysis with the simulation used to train the neural network. And it's also really brittle. Like it's not really guaranteed that it's going to do really well to predict. Like, say you have something that's a little bit different in your like cosmological parameters or initial conditions, it's not really guaranteed that it has learned the physics rather than just an interpolation between your data. And so it's a bit difficult to do this. But in recent years, there's a bunch of very smart people that have worked on using like GPU computing to code the physics that we know to work on GPU. And that has really changed the game in terms of making the model faster to learn. Instead of running the same simulation on the CPU, we're running them on GPUs now, and it makes everything much faster. So we thought, all right, so what can we do? So this is, okay, so let me just explain to you a little bit more the idea that we've been having for this specifically. So what we can do is we have those equations. This is a fancy way of writing F is equal to ma. So this is the equation for gravity that we have to solve. So the force is equal to the mass times the acceleration, which is what you learned in high school physics. So the force is gravity, and the acceleration is how particles need to move. So the way that an n-body, like a gravity simulation works is you have a bunch of particles and they interact with gravity. So every step of this simulation, you need to calculate the force between every pair of particles. And then you know the total force on one particle, you can move it one step forward in time. And you do that for all your particles, and then you can move them all one step forward in time. Then you do it again. So you calculate the force between every pair of particles, you calculate the total force on every particle, you move them one step in time. So it's really long because it scales like n squared, which is the number of particles squared. So the more particles you have, the longer it is. So it's not an efficient way of doing simulations. But one thing you can do is that you can actually take all your particles and project them on a grid, and then calculate a potential, a gravitational potential. And then it makes it much faster to calculate the force, because you can use the fact that the force is the gradient of the potential. So this is what I'm writing down here. And then if you do that and you run your simulation, it looks like this. This is the full one if you had taken all the actual forces, and this is the one if you had taken just the gradient of the potential. And I don't know if you can see, but it's a bit more blurry. And the reason why it's blurry is because when I projected in the positions of my particle on the grid to get my potential, I lost track of exactly where my particle was on the grid. So I lost some information about the very small scale in my simulation. And that's what's causing the blurriness. So on really small scales, it's not really good, but it works well on large scales. So then what we thought we should do is actually train a neural network to correct this evolution equation. So not a neural network that corrects like the whole simulation. It takes all the physics we know, it just corrects it a little bit for the fact that we're making an error when we're smoothing on the scale of 1 pixel. And it corrects the evolution equation. So we can consistently use this new equation to do the prediction. So we can put a neural network inside our equation, learn the correction, and then we get a not blurry simulation. And then that's much faster because it scales as fast as the projection with the gradient of the potential, but it's as precise as if we had the whole simulation. So, okay, so this, I'm going to skip that. So, all right, so now we have a way of getting the particles. We have a way of getting the dark matter. We need a way of putting the galaxies on top of that, because what we see in the universe are galaxies. So we need to, that's called in-painting. So we're painting the galaxies on top of the dark matter. Okay, so how do we do that? So there's multiple ways that have been proposed to do that. One really fun way is with something that's called diffusion model. So it's generative modeling. And you've probably seen things like that. So these really look like people, but they're not actually people. They're fake people. So if you have played with Midjourney or like Sora or Nano Banana with Gemini, maybe you have come across these things. You can make those like ChatGPT and large language model, Gemini, and all these things generate like new images by prompting, by just like make an image of somebody eating pizza, and then it makes that guy. So that's not like a real person. It's just, it's been trained on the image of people, and then you give it a phrase like a sentence, and then condition on that sentence, it can generate an example that looks like all the other examples of people that it's seen before in that context with that pizza. So we can do the same thing with galaxies, but instead of conditioning on like one sentence, we can condition on our map of dark matter. So because for this map of dark matter, I have run a certain number of like full hadron simulations that have the galaxies, put the galaxies on that map of dark matter. Like give me the map of the galaxy that corresponds to that map of dark matter, the same way that I can say to Gemini, give me like an image of a guy that looks like he really likes pizza corresponding to that sentence. So I just replace the sentence like a guy that likes pizza by the specific map of dark matter. And that's what I can do. So basically it maps like just noise to the distribution of galaxies that I want. And I'm just going to skip to that very fast, but this is the comparison between like what you would get with traditional approximations that we can run versus like what it actually does, and it works much better. And we get much more accurate results than with like usual approximations that are extremely crude because it's really expensive to paint those galaxies on dark matter. And so when we run our inference at the end of the day to try to measure what are the parameters that give rise to like our simulation, this is all mocked, it's not real data, it's just mock data, like fake simulations. But we find that we can get more information out of our simulations than what we could with traditional methods, and it's also much more accurate. So there's less chance that we get the wrong answer and we don't know that we're wrong. So we get good uncertainties around the right answer, which is what we want. So it's really promising for applying this to real data. So we're still making sure so this is on simulations. They're not fully representative of what we're going to get in terms of data. So we're still developing those methods, but it's really promising to scale to much larger volume to be able to analyze all the wealth of data we're going to be getting in the coming years. All right. So next problem that we have to solve. I'm out of time, but I can keep on talking if you guys want to. we have to chat until like 8:30, so I can keep on going, right? Okay, so it's a problem of foreground contaminants, right? And I said, like I mentioned, they're about like 10 to the times larger than the signal that we care about. So that's a problem that's like much more general than that. Like the problem of like additive noise is a problem that's really common in a lot of fields. So it's also a problem that we have in astronomy. So this is what we call the Gaussian noise. It's a form of noise that you might have encountered if you take photos at night. If you have a really old phone, maybe you've seen that when you try to take a photo like late at night, it kind of looks like this. But what your eyes see is like this. It doesn't have all the like noisy thing. That's because of noise on the CCD of your phone. So we have the same thing in cameras that we use to look at this guy. And it's specifically apparent when we have like low light photos. This is another example. So there's a bunch, if we zoom in like parts of the water there, we see that there's, again, this noise that's there, but there's also other artifacts, like there's pixels that are very white. They're kind of also artifacts. We also have those. They're called hot pixels in our telescopes. We also have those. And so if we look at something that's like a galaxy, typically it's going to be kind of low light because it's dark. There's not a lot of light that comes from galaxies. So this is going to be a really big problem. So if we had like white noise, and we looked at like something, say like the picture of a guy, it would look like something like that. And we have methods that can take this into account. So that introduce uncertainties in what we try to measure because there's less information in it. It raises a lot of information, so it increases the uncertainty on what we try to measure. Like say we wanted to know what's the size of the face of this guy, it would be more uncertain than if there was less noise, for example. But all the methods that we have, typically, they assume that the statistics of this noise is Gaussian. Gaussian means that it's like white noise. It just looks like that. Now I'm about to show you real noise from real telescope and tell me if you can see the difference. This is real noise. There's no signal here. It doesn't look really like this, right? It looks very different. So this is the Hubble Space Telescope. These are two different patches of noise. Like there's no gas, there's nothing there. It's just noise. The bright patches are cosmic rays, so they're very energetic particles that hit the CCD and they just deposit a lot of energy in there. And this is the James Webb Telescope. It has these like stripes, and like the bright spots are again cosmic rays. There's these really high energy particles that just hit the detector, and the stripes, they are just noise. They come from reading the CCD. So clearly this does not look like Gaussian noise whatsoever. So all the fancy, beautiful methods that we have to analyze the data, they're just not going to work here because our noise is just not Gaussian. So all the approximations we make, they're all going to break when we make contact with reality. So sad. But the thing that we realized recently is that we have these very powerful generative models that are trained to approximate the distribution of anything. That's how we can like generate new faces of people. We look at a bunch of examples of faces of people, and then we learn the distribution of like if every pixel in an image is like a dimension, in like 100 by 100 pixels, like a 10,000 dimensional space, right? And so in this 10,000 dimensional space, there's like a manifold that represents the faces of people. This is where all faces of people live. There's like specific values for pixels that represent faces. So if I want to learn what's the shape of this manifold, I can then generate new samples of new faces of people. This is how a generative model works. So I can do that. I've learned that for people. Maybe I can do that for noise as well. In this like 10,000 dimensional space, there's also a place where noise lives. And so if I learn the shape of this weird shape of noise here, then I can represent this distribution with a generative model. And I can learn, so by learning this new distribution, I can use that learned distribution to analyze my data and get the right measurements that's not biased out. So we can do that. And then using a generative model trained on noise, we can generate new examples of noise. So this is fake noise at the bottom. It really looks like the real noise, like it's super realistic. It's just not real noise. It's fake noise, those two and those two. It's new real, they're not the same, they're different, but they come from the same underlying distribution, like in this really high dimensional space. So what I can do is I can use that to make really realistic simulations of noise. That's going to be really useful if I want, or I can use that to analyze my data, to marginalize over this like nuisance effects, to see like what's the information that's been destroyed by the noise, by the detector, and what's the information that's preserved. So I'm not going to go into details, but just like at the bottom here, this is called the corner plot. So the orange is the real parameter that I've injected in like a real image, a real patch of noise. And if I had done this analysis with traditional methods, like assuming that I have Gaussian noise, the parameters I would have thought are generating this data are the blue circles. So you see how they're really off compared to the cross? So that's, and I would have thought that this is the reality with those uncertainties. I'm really far off. Like, this is really bad. Like, you don't want to be confidently wrong. Like, these are the worst kind of people. The people that are wrong and very confident that they're wrong. This is just not good in science. You never want to be in that situation. But then if you use this learned model to do the inference, you get the gray contours that are like really consistent with the orange cross. So then you're a bit more uncertain, but you're not wrong, which is really important in science. So you can do that like statistically. So these kinds of methods, I think, they work with anything that's additive on top of the image, and specifically like the foregrounds is something that gets added on top of the signal that we care about. So this is the kinds of methods that are going to be really useful to subtract foreground from cosmological signals that we care about in the next decade. So with this, I hope that I've convinced you that with machine learning models, we can extract a lot more information from the data we're going to be getting, and we're going to be in position to learn a lot of super exciting things about our universe in the next 5-10 years. So with this, I'm going to thank you. 5-10 years.
Now just question time. So
We also had a bunch of questions.
yeah.
Do you guys have questions? Yeah.
Sorry, what's CCD? Is it something about the noise from a camera? Or...
Yeah, so the thing that takes photos here, this is like the thing that captures like the light, is called the CCD.
What is it short for?
Oh my God. Charge coupled device. That. Yeah, and then they're basically the same things that we have. It was developed by an astronomer actually. So we have really like big, large CCDs with a lot of pixels for a bunch of like data that we take. So the CCDs are like the things we use to take data in visible light. There's different types of detectors that we use to take data in a sub-millimeter light. They're read differently as well. But yeah, it's the same kind of like the thing that's in your phone is basically the thing that's in LSSD. There's just way many more pixels in LSSD. Yeah.
You can only think in terms of the pizza guy. I can't get to the next step. So staying with the pizza guy.
Yeah.
If you say your model produce a man.
Yeah.
You're gonna get random men photos or random men pictures. Picture a man with pizza.
Yeah.
You're gonna get men with pizzas.
Yeah.
Picture a man with a pizza with glasses.
Yeah.
You're gonna get man with a series of men with pizzas. So what you're doing is you're going in and you're telling it what you want it to look like.
Yeah.
And then it's designing the image.
Yeah.
Okay.
But it's not really designing the image. It's really like because the first step of all these things is the training part. That's the part that's like really important. So the training part we had like
Stuff that you see.
yeah. So basically it's really like the really key to understanding machine learning is understanding that like an image is really just a vector in really high dimension. Because like every value of pixel is like one dimension in this vector space, right? Like if I have an image, every pixel has an intensity value, right? If it's a black and white picture, like every pixel has a value between like 0 being black and like, so it has like a value, right? Every pixel. So I can put those in a vector and then I can represent that like as an arrow. So that one image is an arrow in like, if I have 100 by 100 pixel, it's like an arrow in a 10,000 dimensional space.
But you create a picture one time, and the piece of pepperoni is sitting here,
Yeah,
and you do it the next day, and the
Yeah.
piece of pepperoni is gonna be in another place.
yeah,
Okay, and his nose is gonna be a little different.
yep,
So taking it to your dimension.
Yeah.
Every time you ask the question, it's going to be a little different.
Yep.
And so how do you know when you're converging on what the real pizza guy looks like? And whether it's got a pepperoni pizza in it?
okay, so yes. So there's like two different, so for the case of like in painting the galaxies, there's a lot of stochasticity in even like the real models. So basically every time that you get like the piece of paper in here or there or there or there, these are all possibilities that are consistent with a guy with a pizza, right? So for me, it's like they're all consistent with the dark matter map that I gave. So I want to get all of those and I want to incorporate those as uncertainties in my model. So I know that like the piece of pepperoni is never going to be on the head of the guy. Like it's very unlikely, but it could be somewhere on the pizza. So in a similar way, I could have a galaxy that's like inside the dark matter nugget, but it's never going to be like in the void, for example. So, and then those uncertainties, I definitely want to take those into account because they're part of my modeling uncertainty. So when I compare with observations and I've seen say 5 galaxies in that halo, and like I want to say, okay, this possible like cosmological model can predict between like 2 and 10 galaxies in that halo, then I know that these two are consistent. But if I have a simulator that predicts that there should always be 100 galaxies, between 100 to 150 galaxies in that halo, and I observe 5, then I know that there's some inconsistency. Maybe fun. Marco, yes.
When you go to the training sessions, are the parameters free or are you able to put in any a priori information? Because that makes a big difference, I think.
So it's so the way that you build the a priori distribution is when you build your training data. So the training data, it's assumed that training data are samples from the a priori distribution that they have to be like identically distributed samples, identically distributed independent samples from the distribution you're trying to represent.
The structural information that a priori will be in the training data.
Yeah.
That can restrict just a free.
Yeah. And then there's another way that you can impose like a priori information is in the structure of the neural, like the architecture of the neural network that you build. So if you build a neural network that has a certain type of architecture, for example, there's some information, some distributions you're not going to be able to represent.
Right.
Or conversely,
so with your astronomical data, do you do so? How do you do that?
So there's a bunch of people who tried to say, they said, okay, so there is a bunch of things we know about the universe. Like we know that there's a translation symmetry, there's a rotation symmetry. The galaxy doesn't matter if they look like this or like rotated, they can be flipped. There's a bunch of symmetries that we know exist in the universe. So we could just try to incorporate that directly into the architecture of the neural networks, just not to have to like just have so much more examples in the training data that would just have the same information, but have to learn it inside the neural network. But it turns out that every time that somebody tries to come up with these like invariant neural networks, these invariants have to hard code them in the neural network. It turns out that training is so much harder than just like empirically imposing it through like data augmentation in the training data. So like it was a really nice idea. I would have loved it to work, but it just turns out that it's easier to just impose those symmetries at the level of the learning data. Yeah, but it's like a bunch of people like tried to do that really hard for many years. And maybe there's better ways to do it that we just have not figured out yet. There's a bunch of people doing research in that area. But it looks like it's easier to just enforce it at the level of putting data augmentation in the training data in practical levels. Yeah. Yes.
Do these models sometimes make stuff up?
Yes. But that's the reason why you want to have your uncertainties as well, right? You want to have all the samples of everything that's consistent with the data that you saw with with uncertainties. So if you have like, there could be like a galaxy in the shape of a cat, but then I do a bunch of like samples. So it's like, and then I just look at like what galaxies are consistent with the data that I saw. And out of like 10,000 galaxies that I generated like that, there's only one of them that looks like a cat. I mean, there's 1 out of 10,000 chances that this is what reality is. So it's much more likely that actually it's not a cat than a cat. It could be, but it's very unlikely. Like I would have to have like a really weird realization of noise in my telescope. Like that's what people mean when they mean like 3 sigma detection. It's like a 1 in like it's 99.997% chances that it's a thing I say, but there's also some chances that it's not, just because of statistics. So that's why it's so important to have like uncertainties, because if you have the one sample that looks like a cat, you're not going to be confidently wrong. You're going to say, yes, it could be a cat, but also it's very unlikely. Yes.
Thanks a lot for your talk. It was really interesting. I have a question about the beginning of your talk when you talked about the CMB background and how there's different temperatures there, and that's caused by dark matter. And so I was wondering if you knew about what dark matter is distributed like in the early universe and why it could be distributed in that specific way.
Yeah, so the way that it's distributed is like, so inflation is a thing that gives us the initial fluctuations in temperature. And the thing with dark matter is that it has a much better memory for where those fluctuations were compared to regular matter, because it was coupled with photons. So photons kind of smeared out stuff a lot. So it would have erased a lot of the fluctuations. But because we know where dark matter's fluctuations are, we can measure those fluctuations. It looks like it's a lot. It's because of dark matter, basically. So yeah, just give me 1 second. I'm gonna pull a different talk. This is, oh no, we're gonna stop sharing. We're gonna do something that I'm not supposed to do. Wait. Just give me 1 second. I have to think about where that talk is. No, it's not here. It's here. It's in this one here. Okay, so the plot that I'm going to show. Okay, now we have to go back here, share again. Okay, this. All right, so this is the CMB. Okay, so what I can do is I can pick like for a specific size of fluctuation, I can look how many fluctuations there are of this size and then just add them all up. And then go to next size and measure how many fluctuations of that size there are and then add them all up. So you see that there's some like preferred sizes. Like for example, like the big blue spot here at like that size, there's a bunch of those, right? Like they're kind of like repeating in pattern. And there's another preferred size that's about like, this big. And if you just go around, there's like a lot of fluctuations of that size, but like really, really small, there's not that many. They just look like there's some smoothing scale kind of in there. So if I just make that graph of like size of fluctuation versus how many there are on the y-axis, what I get is this. Okay, so this is like how many fluctuations there are on the y-axis versus the scale of the fluctuation on the x-axis. So big fluctuations are there on the left side and small fluctuations are there. So this thing that I was saying, I think there's not that many small fluctuations. It's like this end of that graph. And then you said there's this big like preferred size of fluctuation here. Okay, and in blue is like the prediction from inflation, and the red marker is the measurement from that graph that I just showed. So like the two, they really agree like really, really well. Okay, but then the key here is that if I look at the size of that peak here versus the size of that peak here, okay, they would be very different if there was not dark matter. So to have the specific ratio of those two peaks, you need exactly the right amount of dark matter. You need exactly 5 times more dark matter than regular matter to get that ratio. So if it was not for dark matter, this peak would be much lower and this one would be much higher. So this is how we know that is there from this graph. Yes. Yeah, that's what we're just talking about. Yeah. So exactly. So that's why I want to, so the way that we want to be using machine learning in sciences is we don't want to be using like point predictions that are very like, unique answers where we don't have an idea of what's the uncertainty around that answer. Because then there's a very good chance that we're going to be confidently wrong. And this is very bad when we're going to be doing science, right? So we really want to understand those predictions within a statistical framework. So we want to understand those models as statistical models and understand their uncertainties and quantify them in a way that we can show that it's accurate. Like when I say there's like 1 sigma, like there's 68% chances that the answer is this, I want to make sure that it's actually 68%. It's not like something different. So we do a lot of work in my group specifically where we try to develop methods that can measure that. Like, are the things I'm generating, are they from the distribution that I think I'm generating from? And like, how wrong am I, basically, in the distribution that I'm sampling? So that's called accuracy of uncertainties. And so we make a lot of effort to make sure that we have ways to trust that the samples we're generating are accurate. So it's okay to have, a couple, like, you can have like one hallucinated sample if you have the right proportion of sample that's like correct, basically, if it's consistent with your data. And that's going to allow you to say with what confidence this is the answer in a way that you're not going to be wrong. Yes.
Thank you for the talk. I had a question about systematic biases.
Yes.
Do they ever happen? And if so, how do you do?
Yes, the answer depends on what the systematic bias is. But like the thing I was talking about the noise, this is a thing that's been common. It's been very common in astronomy in general, that it's a very difficult bias to take care of because you need to like correct for the noise, then you subtract the noise, but you can't really subtract the noise because the noise has destroyed information. So like you're going to be overconfident because you think you have more information than you really have because information has been destroyed, but then you're so this way of doing it is actually allowing you to have less systematic biases because you're like marginalizing over the whole distribution of noise to know all the possibilities that are consistent with the data that you did measure. So it's actually, if you frame it in the correct statistical framework, you're going to be more like, it's going to be more statistically accurate. Now, there's a bunch of different methods depending on that are very dependent on your training data. And then what if your training data is wrong? And then not wrong, like, for example, I can say, okay, I'm going to train this like simulator machine with the simulations that I have. And I'm going to use that to analyze data from the universe. Well, I know my simulation is wrong, like at some level, like I know my simulation is not perfect. There's a bunch of approximations that went in there. There's a lot of physics that I don't know that goes on inside galaxies that influence what happens on like larger scale, what galaxies look like. This is not a perfect simulator. So it's going to change, it's going to bias my answer like with a systematic bias in a way that's going to be very hard to quantify. And so this is an open problem that we actively do research on. It's also a problem with traditional methods because like if your simulator is wrong, you're going to have wrong results. But there are ways that we're developing to make our analysis method more robust to those kinds of systematic biases. Yeah. Yes.
How precisely have we been able to map the distribution of government in the executive?
This is a very broad question. It depends on the scale of, like in strong lensing data, it's like it's a scale of a galaxy, right? So it's like within the scale of a galaxy. And we have been analyzing archival data because it turns out there's a lot of information in archival data that we had not been able to extract before. But now that we have more powerful methods, we can extract more information. And it looks like we can be much more accurate than what we thought we were before. So yes, very small scales, but this is not like cosmological survey scale. So there's an expert. Oh, she just left. She doesn't want us to ask her question. Justin is an expert on weakness. So she actually is in the business of mapping the universe, the dark matter in the universe on really, really large scales. Yeah, very large scale maps of the universe. but yeah. More questions? Yes.
In that experiment where you showed that the energy, dark energy stays constant despite the density, then how would people figure that out? Like, is there a way to measure the dark energy?
It's just, you know, it's kind of like what you need to put in the equation for it to give the effect that we see. So it's very like, yeah, it's the term we plug in the equation. So it gives what we observe, but it's not like we don't know what it is. It's just very counterintuitive. Yeah, it's just the term you plug in the equation. That's what it does. And it explains the equation, the observations. Yes. You have more questions now? Okay, I thought you had raised your hand. Sorry. Is there more questions? Yes.
Are there any similar candidates for probability, or do you really like have zero?
There's a bunch of theories. There's a lot of different theories. But it's just so weird. Like, I don't know. Maybe Robert knows more about this than me. So we can ask Robert after.
The only thing that would
But yeah, it could be like, I mean, it could be very boring. It could be just like a cosmological constant. But it's looking like it's not that, maybe potentially. So that would be exciting. But it's, yeah, no, it's like there's a bunch of theoretical possibilities, but we don't have a lot of evidence for observations. So, you know, it's very easy to come up with a new theory. It's very, very hard to go out and test it or rule it out. And so there's like a gajillion theories, but not a lot of evidence. So it's really like we really need to get more data and put constraints on what it can and cannot do to really be able to learn more. Yes.
It'd be like emerging.
What?
Dark energy could be emerging from something else.
Yeah, it could be. Could be something dynamical. It could be a new kind of stuff, or it could be that gravity is wrong and it's something different than gravity on very large scales, like something different than GR on very large. It could be, but turns out that that is really hard to make work well mathematically. So it's a bummer, but that's what it is. Yes, you had a question out there?
Well, I was be the last one, so. Yeah, well, I can. It's fine, I was just wondering what your favorite dark matter candidate was.
Oh, my favorite?
Yeah.
Oh, I don't have a favorite. I'm just really, you know, it's one of those like really fun because the predict like the leading model, like the favorite model, the standard model is like it's cold dark matter. And cold dark matter predicts that there should be a gajillion subhalo. It should be like super, super bumpy. The foot of the wine glass should be like full of clumps. And that should give a really, really big signal on data. So like we should be able to see it. So like the favorite candidate of everybody is that we should see a lot of signal in lensing. And then it's really exciting because nobody's really been able to see it so far, but because we didn't have good analysis methods really. So now that we're developing good analysis methods to be able to extract that signal, if we don't see it and we know that we should have seen it if it was there, it's even more exciting because then it means that it's really like new physics. So we rule out the leading model. So that's kind of like really exciting. But I mean, it would also really be exciting to like confirm cold dark matter. So yeah, it's just a fun problem because like whatever we find, we're guaranteed that it's going to be exciting. Yeah.
Okay,
So yeah, so like in the beginning of the talk, there was like there's actually another public talk that's happening on April 9th. So yes. So it's the Anna McPherson lecture. So for the public talk is April 9th. It's going to be in LeCoq 132. I think it's going to be on that side of the building. So yeah.
Speaker is Alessandra Buonanno, who is director of the Max Planck Institute for Gravitational Physics in Berlin, and she's an expert on gravitational waves. So it will be on gravitational wave